We have looked upon the world, upon the sky, and woven narratives from the threads of light and shadow, seeking patterns in the chaos, meaning in the void. For hundreds of thousands of nights, a sentient species, born of water and stone, looked up at a bright, steady point of light in their sky, a celestial wanderer that outshone all the fixed stars, a beacon of constancy in the turning vault of heaven. It moved with a slow, regal patience against the backdrop of the zodiac, a traveler following its own secret laws. They named it for their king of gods, for the arbiter of fate, the wielder of lightning, the chief among deities who ruled from a distant throne. Jupiter, to the naked eye, unaided by glass or science, it was just that, a pinprick of intense, unwavering brilliance, a dot of resolved light, a pearl set in deep velvet. But within that dot, within that singular point of light, perceived by generations of poets, farmers, kings, and priests, lay an entire cosmos of impossibility. A world so vast, so alien, so violently contrary to every instinct born of our terrestrial experience, that to call it a planet almost feels like a failure of language, a diminishment of its sublime and terrifying reality. For generations, we told ourselves a simple story about this distant giant. We called it a gas giant, a colossal sphere of stormy atmosphere, perhaps with a solid heart of rock and iron buried deep within its cloudy depths, a larger version of the familiar, scaled up to a mythic proportion. It was a tidy explanation, a sensible extrapolation from the world we knew, a projection of our own planetary identity onto the unknown. But the universe is under no obligation to be sensible. The universe specializes in the sublime, the strange, and the violently beautiful. It operates on a logic written in the language of extreme physics, in the mathematics of chaos and complexity, in the silent, cold equations of gravity and quantum mechanics. And Jupiter, as we have come to understand in the brief, flickering moment of our scientific awakening, is its masterpiece, a masterpiece that rewrites the definitions we hold dear. The truth, as it so often is when we peer deeply into the heart of things, is that almost everything you were taught in school about this planet is a graceful, well-intentioned fiction. Jupiter is not a giant ball of gas. That simple, comforting phrase, repeated in textbooks and planetariums for decades, obscures a reality far more wondrous and far more terrifying. It is a placeholder for ignorance, a label that masks a profundity we are only beginning to grasp. Jupiter is an ocean world, a realm of liquid so profound it dwarfs all earthly seas into insignificance, a global abyss that contains volumes beyond human comprehension. And as if that fundamental reimagining were not strange enough, we must venture further into a territory that defies the very categories of our experience, into a realm where matter itself is forced into new identities under the tyranny of pressure. For the greatest ocean on Jupiter is not made of water, it is an ocean of liquid metal. Beneath those iconic swirling clouds of ammonia and water ice, churning in perpetual tempests wider than our own planet, lies a descent into a state of matter that exists nowhere naturally on Earth, a descent into a realm of pressure and heat so extreme that the most abundant element in the universe, humble hydrogen, is forced to shed its familiar gentle identity and become something entirely other, something exotic and gleaming. This is not merely a planet in the sense that we understand a planet to be. It is a laboratory of extreme physics operating on a planetary scale, a chronicle of the solar system's violent and messy birth, written in its layered interior, and a living question mark hanging in the void. Its true nature is one of the deepest, most resonant mysteries in our celestial neighborhood, a mystery that has only begun to unravel in the fleeting moments of our own scientific awakening, a puzzle whose solution may redefine our understanding of how worlds are made, not just here, but around every star in the galaxy. Our journey to understand this colossus begins not with a revelation, but with a glimpse, a first tentative, grainy look that raised more profound questions than it answered. This image, a mosaic of light and shadow, rendered in the stark contrasts of early digital photography, is the first close-up portrait of Jupiter ever taken by human eyes, or rather, by a human-made instrument. It was captured by a humble pioneer, a spacecraft named Pioneer 11, in the closing days of 1974. To modern eyes accustomed to the crystal clarity of the Hubble Space Telescope or the Juno spacecraft, it might seem primitive, a blur of banded ochre and white, lacking in fine detail. But in that moment, for the scientists staring at the data streaming across light minutes of space, it was nothing short of a revolution. For the first time in the long human story, the dot resolved into a world. We could see the structure of its clouds, the stark boundaries between light zones and dark belts, the hint of its great storms. It was real. It had texture, form, dimension. It was a place. And then, just a few years later, came an even more profound gift, the first moving picture, a time-lapse sequence from Voyager 1 as it approached the giant in 1979, a silent film of otherworldly majesty. The planet turned. The Great Red Spot, an ancient hurricane already centuries old, slid into view from the limb, a colossal eye staring back at the intruding spacecraft. Swirling cloud bands churned like fluids in a titanic basin, streaming past each other in opposing jets. It was alive. It was dynamic. It was a fluid sculpture in motion, breathtaking in its scale and complexity. But therein lay the problem, the beautiful frustration of science. Beyond their undeniable aesthetic power, beyond the awe they inspired in the public imagination, these initial portraits provided no definitive answers about the true fundamental nature of the gas giant. They were, in essence, studies of a surface that was not a surface. They detailed the symptoms, the cloud patterns, the wind speeds, the storm dynamics, but gave no clue to the underlying anatomy, the deep structure, the composition and state of the material beneath that shimmering veil. They only deepened the enigma, raising profound and unsettling questions that would drive exploration for decades to come. What is this thing made of, truly, beneath the clouds? Is it all atmosphere, a vast puffy sphere of gas with nothing substantial beneath, a celestial cloud with no bottom? How did it get so impossibly big, accumulating more mass than all its sibling planets combined? What forces, what processes in the early solar nebula could assemble such a behemoth? And what does its very existence tell us about the story of our own solar system, and by extension, about the formation of planetary systems throughout the galaxy? The images from Pioneer and Voyager were a door cracked open, revealing a chamber of such staggering scale and complexity that our minds calibrated to the gentle dimensions of mountains and oceans, to the thin skin of our atmosphere, could not initially comprehend its dimensions or its essence. We saw the painting, but we did not understand the canvas, nor the paints, nor the artist's intent. The actual size of Jupiter is a constant gentle assault on human intuition. We can recite the numbers, commit them to memory, but they slide off the mind like water off glass, failing to leave a permanent impression of the reality they represent. It is not merely large, it is dominant, a gravitational patriarch. It contains more than twice the mass of all the other planets in our solar system combined. Pause to consider that. Take the rocky inner worlds, Mercury, Venus, Earth, Mars, their iron cores and silicate mantles, their mountains and canyons. Take the ringed jewel of Saturn with its own immense bulk. Take the icy tilted Uranus and the windy Neptune. Combine them all. crush their substances into a single sphere, and Jupiter would still outweigh that composite by a factor of 2. It is the gravitational anchor of our planetary system, the silent shepherd whose immense pull has shaped the architecture of our cosmic home for over 4 billion years, clearing debris, stabilizing orbits, and potentially shepherding comets both toward and away from the inner worlds. In terms of sheer volume, the numbers become even more abstract. You could fit over 1,300 Earths inside its bulk. But numbers are abstract, mental shortcuts that often bypass the emotional centers of understanding. To grasp its scale in a more visceral way, we must shrink our world to a more relatable proportion. Imagine the Earth with all its continents and oceans, its mountain ranges and deep-sea trenches, its sprawling civilizations and vast empty deserts, reduced to the size of a single grape, a delicate blue-green sphere held between your fingers, its atmosphere a thin, invisible sheen. On this scale, Jupiter would not be a melon nor a beach ball. It would be a full-sized basketball, a vast striped sphere of dynamic atmosphere, its diameter dominating the space between your hands. And within that basketball, the grape that is Earth would be lost, a speck of dust swirling in an atmosphere of incomprehensible depth, a mote in a colossal eye. This is the scale we are dealing with, a realm where our entire world is reduced to a trivial detail. For decades, our general theory of solar system formation, a theory built on observation, physics, and a degree of elegant extrapolation, provided a seemingly elegant, step-by-step recipe for building a Jupiter. It is a story of patience and gravity, written in the dust of a primordial disk, a narrative that felt satisfying and complete. Our story begins not with planets, but with a majestic swirling disk of gas and dust, a protoplanetary disk orbiting our infant sun, a relic of the angular momentum from the collapsing cloud that gave the sun birth. Within this disk, microscopic particles of rock and metal and ice, the leftovers from the star's birth, the ashes of earlier stellar generations, drifted and danced in the thin haze. Over millions of years, a slow, stately, almost bureaucratic dance of accretion began. These tiny motes, through electrostatic forces and gentle sticking collisions, began to cling together. Dust became pebbles, pebbles became boulders, boulders became mountain-sized planetesimals. And as these objects grew, their gravitational influence began to reach out, pulling in more material, accelerating the process from a slow accumulation to a runaway growth. It was a celestial snowball effect, with gravity as the ever-steepening slope. According to this orthodox core accretion model, Jupiter's story is one of precocious ambition, of being in the right place at the right time with the right mass, in the cold reaches beyond what we call the frost line, the distance from the young sun where water and other volatiles could condense into solid ice. Material was more abundant. Out here, water existed not as vapor, but as frost, greatly increasing the amount of solid material available to stick together. Here, a particularly lucky or greedy core of rock and ice managed to grow faster than its neighbors, voraciously consuming the planetesimals in its path. It reached a critical threshold, perhaps 10 times the mass of Earth. At this point, something extraordinary happened. Its gravity became powerful enough to no longer just attract neighboring rocks and icy chunks, but to start dynamically capturing and holding on to the vast light reservoirs of hydrogen and helium gas that still swirled in the disk. This was the tipping point, the moment of planetary puberty, where it transformed from a large terrestrial body into something else entirely. Once it began, there was no stopping it. The nascent Jupiter became a gravitational vacuum cleaner, hoovering up the primordial atmosphere of the solar system, growing at an exponential, breathtaking rate. It fed for millions of years, until it had consumed most of the available gas in its orbital lane, leaving behind only scraps for Saturn, Uranus, and Neptune to collect in their more leisurely, impoverished fashion. This theory is clean, logical, sequential, and profoundly Earth-centric in its thinking. It implies a neat, orderly layering, like a Russian Matryoshka doll, a massive, dense, solid core of rock and metal, perhaps 15 to 20 times the mass of Earth, a terrestrial planet in its own right, buried at the center. Around that, an unimaginably deep atmosphere of hydrogen and helium, compressed by gravity into thicker and thicker states, but ultimately just an envelope, a garnish, however massive, around a solid planetary meal. This core, if it existed, would be a fossil, a pristine relic from the solar system's first moments, a time capsule holding the secret ingredients, the isotopic ratios, the raw materials of our cosmic beginnings, untainted by the intervening eons. It was a beautiful story, but nature is rarely so tidy, so obedient to our desire for neat narratives. An alternative theory, born from the understanding of how stars themselves are born, offers a different, more fluid genesis. What if Jupiter did not form from the bottom up, from dust to rock to gas giant, but from the top down? Imagine, just beyond the fringe of the early solar system, a separate, wandering cloud of gas, a cosmic eddy in the larger flow of the galactic nebula, a knot of instability. This cloud, under its own weak self-gravity, begins to contract. It grows denser, hotter at its center from the conversion of gravitational potential energy. It begins to spin, conserving angular momentum. This is precisely, step for step, how a star is born. But this cloud is too small, too impoverished in mass, to ignite the sustained nuclear fusion of hydrogen into helium that defines a star. Instead, it undergoes a gravitational collapse that halts as it becomes supported by the degeneracy pressure of electrons, condensing directly into a giant fluid sphere of hydrogen and helium, a failed star, a brown dwarf. According to this gravitational instability hypothesis, Jupiter may have begun its existence not as a rocky seed in a disk, but as a sovereign self-gravitating entity, a sibling to the Sun, in formation, not a child. It would have condensed directly from the nebula, a fragment of the same cloud that birthed our star, and then been captured by the Sun's gravity, tamed into an orbit, and become a permanent, if subordinate, member of our system. If this were true, the implications for Jupiter's interior would be radical. It would have no distinct solid core at all, no fossil seed. Instead, it would be a nearly homogeneous sphere from the start, a layered gradient of gas becoming fluid under pressure, all the way down to its very center, with heavy elements mixed throughout from the beginning. It would be a pure atmosphere, a giant layer cake of increasingly exotic states of matter, with no rocky heart, no central anchor. For a long time, the core accretion model was the champion, the textbook answer. It made intuitive sense. It fit our narrative of planetary growth from small to large, a narrative we see echoed in the rocky planets. It was the theory most of us were taught, the one that shaped our mental image of the giant. And it is not a crazy thing to believe. It is supported by sophisticated computer models and much observational data from other forming stellar systems. But it is also, as we now know from direct measurement, not correct in the simple, clear-cut, layered way we imagined. The truth, as is so often the case, lies somewhere in between, in a territory that is messier, more interesting, and far more challenging to our understanding. Our first real, tangible breakthrough in deciphering Jupiter, in moving beyond the pretty pictures and into the realm of physical interrogation, did not come from a carefully planned laboratory experiment or a slow incremental analysis of telescope data. It came from cosmic violence, a chance encounter of astronomical odds so vanishingly small it feels like narrative contrivance, a deus ex machina written into the script of the solar system, yet it happened, and we were there, just in time to witness it. This is one of those insane coincidences that sound too good to be true, a moment where the universe seemed to offer up a secret if only we were clever enough and lucky enough to be watching. In July of 1994, the solar system staged a spectacle for an audience of one, a curious tool-using species on a pale blue dot. A comet named Shoemaker-Levy 9, after its discoverers, was on a fateful final trajectory. This was no mere speck of dust and ice, no dirty snowball from the Oort cloud. It was a substantial mountain of primordial matter, a frozen archive from the outer darkness, several kilometers across, hurtling through the void. By the time human astronomers found it, its destiny was already sealed, its path irrevocably altered by a close pass to Jupiter years before. The immense, relentless gravity of the giant had already reached out, seized the comet, and stretched it like cosmic taffy. The tidal forces, the difference in gravitational pull between the comet's near side and its far side relative to Jupiter, had been stronger than the ice and rock holding it together. It fractured, not into 2 or 3 pieces, but into a string of 21 distinct fragments, a celestial pearl necklace of doom, each piece still kilometers across, lined up in a grim procession for a sequential plunge into oblivion. The sheer probability of such an event is astoundingly, humblingly low. Estimates, based on cratering records and orbital dynamics, suggest a collision of this magnitude with Jupiter might occur once every few thousand years, perhaps even less frequently. For it to happen in the brief sliver of cosmic time when humanity had developed the technology to see it, to understand what they were seeing, and to record it with a global network of telescopes, borders on the miraculous. It was a front row seat to a cataclysm of planetary proportions, and we were ready. Sort of. The newly refurbished Hubble Space Telescope, its flawed vision corrected by a daring shuttle mission, was pointed towards Jupiter, its instruments primed. But there was a cruel twist of celestial geometry, a reminder that the universe is indifferent to our desire for a good view. The comet fragments were scheduled to impact on the far side of Jupiter, the hemisphere turned away from Earth and Hubble. We would hear the crash, so to speak, through the electromagnetic whispers of the aftermath, but we would be blind to the moment of impact itself, to the flash and the fireball. It appeared we would miss the main event, relegated to studying the scars left behind, like detectives arriving after the explosion. Except, at that exact same epoch, another human-made witness was approaching the Jovian system, its timing so impeccable it feels orchestrated. This was the Galileo spacecraft, named for the first human to turn a telescope towards Jupiter and see its moons, thereby shattering the ancient Earth-centered cosmology and affirming a universe of other worlds. Launched in 1989 on a complex looping trajectory to save fuel, using gravitational assists from Venus and Earth, Galileo was finally arriving at its primary target in late 1995. Its timing was perfect. As the comet fragments began their final fiery descent, Galileo had a ringside seat. From its unique vantage point on approach, it watched the unfolding catastrophe, not with optical cameras primarily, but with a suite of instruments designed to sense ultraviolet light, plasma waves, and dust. What it saw, what its sensors recorded, was a sequence of apocalyptic events unfolding over 6 days in July 1994. 21 separate planetary impacts. The largest fragments, several kilometers in diameter, plunged into the Jovian atmosphere at speeds exceeding 60 kilometers per second. The kinetic energy released was beyond any terrestrial scale, beyond human experience. The largest impact, Fragment G, unleashed an explosion with the energy of 300 million Hiroshima-sized atomic bombs detonating at once. It was by several orders of magnitude the largest explosion ever directly observed by our species, a fireball that, for a brief moment, outshone the rest of the planet combined, a momentary second sun igniting in the Jovian sky, a flash of revelation in the literal sense, as Jupiter's relentless rotation slowly turned the wounded hemisphere into view of Earth-bound telescopes. The Hubble Space Telescope captured the haunting aftermath. The impacts had not merely created transient flashes of light, they had scarred the planet on a scale befitting its size. Enormous, dark bruises appeared in the cloud tops, each one larger than the Earth itself, smudges of black and brown against the striped backdrop. These were not simple soot stains, they were holes punched deep into the atmospheric layers, revealing warmer, darker material from below, or perhaps the chemical residues of the vaporized comet itself. Carbon compounds, silicate dust, lingering in the upper atmosphere. Massive plumes of debris were ejected thousands of kilometers above the cloud tops, material from deep within Jupiter's hidden layers, thrown out into space by the titanic blasts, where they lingered for months like spectral mushrooms, slowly spreading and fading. And this is where the true, enduring gift of this cosmic catastrophe was delivered. The Galileo spacecraft, on its final approach trajectory, flew right through these ejected plumes. For the first time in history, a human-made object was able to directly sample not just the thin, uppermost fringes of Jupiter's atmosphere, but material from its hidden depths, violently excavated and offered up to the void like a biopsy taken by a cosmic scalpel. The data Galileo sent back from this encounter was a treasure trove of confusion, of delightful, paradigm-challenging puzzles. Among the many elements and compounds detected in the impact plumes, sulfur, carbon, silicon, one finding stood out as particularly puzzling and persistent: water. A lot of water. This was deeply strange, counter to the prevailing wisdom. Jupiter, based on its position in the solar system and our models of the solar nebula's composition, was not supposed to be particularly rich in oxygen, the partner element to hydrogen that forms water. It was thought to be a predominantly hydrogen-helium body with only trace amounts of heavier elements like oxygen. Yet here it was, in surprising abundance. Where did it come from? Was it simply delivered by the comet itself, the icy nucleus vaporizing on impact? Or was the comet merely a probe, a geological drill that had punched through a dry layer and revealed that Jupiter's interior, contrary to expectation, held vast hidden reservoirs of water, far more than anyone had anticipated? The water discovery was a clue, a tantalizing, provocative hint that our models of Jupiter's composition and internal structure were fundamentally incomplete, perhaps even wrong. It was weird enough, provocative enough, that it demanded a new mission, a dedicated effort to look past the clouds and into the heart of the giant. Not just an orbiter with cameras, but a dedicated detective designed to peer beneath the veil using the tools of fundamental physics, precise gravity measurement, magnetic field mapping, microwave sounding. That mission was named Juno, after the Roman goddess who could peer through the clouds, veiling her husband Jupiter's mischief, and see the truth. Launched in 2011 on a long, arcing journey, it arrived in 2016, not as a passive observer, but as an active interrogator of the giant's deepest secrets, a spacecraft built to endure the brutal radiation of Jupiter's magnetosphere and answer the questions raised by that chance comet impact 2 decades prior. So when we say that everything you were taught in school is wrong, It is not an indictment of education, but a testament to the relentless, exhilarating pace of discovery. Science is not a collection of facts, but a process of successive approximation, a story we continually rewrite as new data streams in from the frontiers. The real truth about Jupiter, its profound and bizarre reality, did not begin to cohere into a new, consistent picture until this past decade. The simple, elegant story of the gas giant with a solid, dense core has dissolved like a sandcastle under a rising tide, replaced by a picture of far greater complexity, nuance, and wonder. Here, then, is what your science teacher, in all likelihood, did not know at the time the modern understanding pieced together from Voyager, Galileo, Juno, and Earth-based observation. Let us begin at the beginning, at the visible surface, which is not a surface at all, but a ceiling, a swirling, turbulent interface between the hidden interior and the cold vacuum of space. The outermost layer of Jupiter, the part we see through our telescopes, is indeed a realm of gas, but to call it an atmosphere in the earthly sense, a thin, life-giving blanket, is to profoundly underestimate its scale, its depth, and its ferocious energy. These are the iconic banded clouds, the zones of rising light, gas, and belts of sinking heavier material, the ballet of global circulation driven by the planet's ferocious rotation, a full spin every 10 hours, a velocity at the equator that would tear any solid planet apart. Here, in the high-altitude clouds, tens of kilometers above any hypothetical surface, the temperature is a profound and bitter cold, plunging below -100 degrees Celsius. In this frigid realm, water exists, but in a strange, slushy conspiracy with other chemicals, primarily ammonia. Tiny crystals of water ice interact with ammonia vapor. Ammonia, a simple compound of nitrogen and hydrogen, acts as a potent natural antifreeze, dramatically depressing the freezing point of water and allowing for the existence of supercooled liquid water droplets amidst the ice crystals. This ammonia-water mixture is a recipe for powerful electrostatics on a colossal scale. As the slushy hail and supercooled droplets collide in the turbulent updrafts of Jovian storms, they transfer charge just as ice particles do in terrestrial thunderheads, but with far more material and energy involved. But on Jupiter, everything is amplified to a mythic, almost absurd scale. The lightning generated is not mere forks of plasma in the sky. It is continent-sized, a sustained, monstrous discharge of energy that can release 1,000 times the power of a typical Earth lightning bolt, lighting up vast swaths of cloud deck from within. These storms are not occasional weather events. They are the permanent state of being, a perpetual, planet-wide electrical storm raging in the deep freeze, a permanent light show of staggering power hidden within the cloud tops. These towering thunderheads, fueled by immense jets of hot, moist gas rising from the unfathomable depths below, are the engines and the manifestations of Jupiter's most famous feature, the Great Red Spot. We have watched this colossal anticyclonic storm, this giant vortex, for nearly 4 centuries, since Robert Hooke and Giovanni Cassini first noted its presence in the 1660s. It is an enduring tempest, a vortex that has swallowed Earth-sized storms for breakfast for longer than our modern civilization has existed, a permanent fixture in a dynamic atmosphere. Its scale is again almost a parody of planetary proportions, a constant reminder that our home world is a modest place. It is thousands of kilometers in diameter, wide enough to fit 2 or 3 Earths side by side within its swirling maw. But its majesty is not just in its width, its 2-dimensional footprint on the cloud tops, but in its depth, its 3rd dimension. Recent data from Juno's microwave and gravity instruments suggest it is not a shallow skin-deep feature. a mere painted swirl on the cloud canvas. It is a titanic column of rotating gas and cloud that extends at least 300 kilometers down into the planet's atmosphere, perhaps far deeper. It is a rotating skyscraper of storm, its roots anchored in warmer, denser layers below, drawing energy from the internal heat of the planet itself. The spot also reaches higher than the surrounding clouds, its upper deck elevated like a plateau. This altitude is the secret to its haunting, distinctive color. Higher up, it is exposed to more intense ultraviolet radiation from the distant sun. This UV light acts as a catalyst, bombarding chemical compounds within the storm, likely complex hydrocarbons formed from the photochemical breakdown of methane and ammonia, perhaps incorporating phosphorus compounds, or even sulfur dredged up from below, triggering complex photochemical reactions that produce that distinctive deep brick red hue. It is a slow cosmic tanning process, a stain of radiation on a cloud bank 10 times taller than Mount Everest, and whose roots delve deeper than the Earth's oceans are deep. To imagine a cloud formation of such vertical extent, a structure that is simultaneously a storm, a chemical factory, and a historical record, is to strain the very limits of terrestrial analogy. Yet, for all its spectacle, for all its daunting size and longevity, this entire raging, lightning-laced, storm-racked outer shell is astonishingly shallow in the context of the whole planet. The average depth of these colorful ammonia and water cloud decks, the part we can see and that contains the Great Red Spot and the zonal jets, is a mere 50 kilometers. A thin skin, a vibrant epidermis on an organism of incomprehensible bulk. It is the wrapping paper on the gift, beautiful and intricate, hinting at but completely obscuring the utterly alien, unimaginable present within. Below this thin, active layer, the real Jupiter begins. As we descend, leaving the riot of the cloud tops behind, the environment begins a radical, fundamental transformation. The first change is the fading of light. The brilliant yellows, ochres, and whites painted by sunlight and chemistry are quickly swallowed by a deepening amber, then a rich brown, then a perpetual, absolute twilight, and soon an utter, profound blackness. No photon from the sun penetrates more than a few hundred kilometers down. The second, more physically significant change is the relentless exponential increase in pressure. On Earth, we define atmospheric pressure at sea level as 1 bar, the weight of a column of air about 100 kilometers high. In Jupiter's upper clouds, the pressure is already comparable to Earth's sea level, but as we sink, gravity, the master architect of this world, takes over. The collective weight of all the atmosphere above, and there is a truly stupendous, mind-numbing amount of it, presses down with ever-increasing force. The pressure increases not in a gentle linear fashion, but exponentially. At a depth of just a few hundred kilometers, pressures reach hundreds of times that of Earth's sea level, then thousands of bars, then tens of thousands. This relentless compression has a direct and dramatic thermodynamic effect: intense heat. When you squeeze molecules together, you force them into closer and closer proximity, increasing the frequency and violence of their collisions. This molecular violence translates directly into thermal energy, the gravitational potential energy of the planet's own mass, accumulated over billions of years during its formation, is constantly being converted into heat through this process of adiabatic compression, a process with no heat loss. It is a heat engine powered by gravity itself, a furnace with no need for solar stoking. Indeed, Jupiter radiates about twice as much energy into space as it receives from our star, a testament to the primordial furnace still burning in its heart, the slow leakage of that formative gravitational energy. So we descend into a realm of growing, searing heat and crushing, mind-bending pressure, a fog that becomes not just thicker, but fundamentally different in its essential nature. The gas molecules, primarily hydrogen and helium, are forced so close together that the classical distinctions between a gas and a liquid begin to blur, then vanish entirely. There is no boiling sea to break through, no distinct surface tension creating a meniscus against a container wall. Instead, the hydrogen gas, which makes up roughly 90% of Jupiter's bulk, undergoes a continuous, smooth phase transition dictated by the laws of thermodynamics. At a depth of approximately 1,000 kilometers below the cloud tops, the conditions cross a critical threshold. The pressure has risen to such an extreme, to around 10,000 bars, that hydrogen can no longer exist as a gas, regardless of the temperature. It undergoes a transition first to a supercritical fluid, a state that has properties of both liquid and gas, and then decisively, unambiguously into a liquid. This is not a theoretical boundary drawn on a chart. It is a fundamental change in the behavior of matter, a crossing into a new phase domain. We have arrived conceptually at the true surface of Jupiter, not a solid crust, not a rocky shoreline, but the top of the largest, deepest ocean in the solar system, an ocean of liquid molecular hydrogen. This realization forces a fundamental correction to our vocabulary, a shift in paradigm. Jupiter is not a gas giant. That term is a profound misnomer, a relic of an older, more superficial understanding, born from seeing only the outermost veil. It is, in its essence, a liquid planet. The gaseous outer layer is a mere shimmering haze, a wispy, turbulent mist atop a global sea of staggering depth and volume. This sea of liquid molecular hydrogen is about 20,000 kilometers deep. To comprehend that number, consider that Earth's diameter from pole to pole is just over 12,700 kilometers. Jupiter's liquid hydrogen ocean is deeper than our entire planet is wide. It is an abyss that makes the Marianas Trench, the deepest point on Earth, look like a scratch on a dinner plate, a negligible imperfection. This ocean contains more fluid than all the water on Earth multiplied by tens of thousands. But this is where the analogy to earthly oceans, comforting as it might be, completely and irrevocably breaks down, shattering into a new understanding of physical extremes. The hydrogen ocean of Jupiter is a fluid from another physics, a substance obeying rules written under conditions we can scarcely replicate. On Earth, we can liquefy hydrogen in specialized laboratories by making it extremely cold, just a few degrees above absolute zero. Under our gentle 1-bar atmosphere, hydrogen boils at around minus 253 degrees Celsius. On Jupiter, the physics is inverted, turned on its head by pressure. The intense pressure, reaching perhaps 2 million times Earth's atmospheric pressure at the base of this ocean, radically alters the rules of phase transitions. It raises the boiling point of hydrogen so phenomenally high that it remains a liquid at temperatures that would instantly vaporize any known material on Earth: tungsten, diamond, any ceramic. The temperature in this liquid hydrogen layer soars to several thousand degrees Celsius, comparable to the surface of some stars. Imagine a fluid hotter than the lava erupting from Earth's volcanoes, hotter than the surface of a red dwarf star, yet under such colossal, unyielding pressure that it cannot boil, cannot become a gas. It is a superheated, superpressurized fluid, utterly dark, flowing in global currents and massive convection cells, driven by the planet's fierce rotation and the even more intense heat welling up from the even stranger, more alien depths below. It is a pitch-black, seething global sea of primordial hydrogen, a relic of the solar system's birth, still churning billions of years later. And as we voyage deeper, to the very bottom of this 20,000 kilometer deep ocean of liquid hydrogen, the environment approaches the regime of the truly surreal, entering a domain of matter that exists only in theory on Earth and in the hearts of giant planets and stars. The pressure climbs to millions of bars. The temperature exceeds 10,000 degrees Celsius, hotter than the photosphere of our sun, hot enough to vaporize rock and metal. Here, in this inferno, at the base of the liquid hydrogen ocean, hydrogen undergoes a second, even more profound and exotic metamorphosis. It becomes metal. This is not a metaphor. It is not like a metal in its appearance or behavior. It is, in every quantum mechanical sense, a true metal. Under these millions of atmospheres of pressure, the hydrogen molecules are squeezed so violently that their simple covalent bonds are overwhelmed. The hydrogen molecules, pairs of protons sharing electrons, are forced into a new dense packing. The electrons, which normally are tightly bound to their individual protons in hydrogen atoms or shared in covalent bonds in hydrogen molecules, are literally shaken loose by the immense pressure. They become delocalized, freed from their atomic prisons, forming a degenerate electron sea that can flow freely throughout the material, like the electrons in a bar of copper or a lump of iron. This is the defining characteristic of a metal, a lattice of atomic nuclei immersed in a fluid, or in this case a gas, of freely moving, conductive electrons. But here, on Jupiter, the lattice itself is not solid. The incredible heat, those 10,000 degrees, keeps the hydrogen nuclei, which are, for the most part, just single protons, in a liquid state. They are not fixed in a crystalline array. They can flow. So we have a liquid metal, a fluid that conducts electricity as readily as copper wire, a swirling, convective, turbulent sea of protonic nuclei swimming in a quantum soup of degenerate electrons. This substance, metallic hydrogen, is one of the holy grails of high-pressure physics, a predicted state of matter that is thought to exist in the interiors of gas giants and brown dwarfs. It has been created fleetingly in diamond anvil cells on Earth for fractions of a second in microscopic quantities under pressures approaching those at Jupiter's heart, though its exact properties remain the subject of intense study and debate. On Jupiter, it is not an experimental curiosity. It is the main constituent, the dominant material. This layer of liquid metallic hydrogen is estimated to be about 40,000 kilometers thick, wider than the entire Earth from core to surface. It is a churning, electrically conductive dynamo of planetary scale, and it is here, in this realm of liquid metal, that the source of Jupiter's most powerful and extensive external feature is born, its monstrous, protective, and deadly magnetic field. The physics is elegant in its brutal simplicity, a direct application of magnetohydrodynamics. Jupiter's rapid rotation, that relentless 10-hour day, spins this vast sphere of conductive liquid metal. At the same time, convection currents, driven by the intense heat leaking from the core region below, cause hot fluid to rise and cooler fluid to sink within this metallic ocean. This combination of rapid, coherent rotation and turbulent convection in an electrically conductive fluid is the perfect recipe for a self-sustaining dynamo, the same basic process that generates Earth's much more modest magnetic field in its molten iron outer core. But the scale of Jupiter's dynamo is incomparable, truly in a league of its own. Jupiter's dynamo region is not a small shell of molten iron. It is a planet-sized sphere of liquid metal, tens of thousands of kilometers thick, spinning furiously. The resulting magnetic field is the largest permanent structure in the solar system, aside from the sun's own coronal plasma and magnetic fields. If Jupiter's magnetosphere, the bubble of space dominated by its magnetic field, were visible to the naked eye from Earth, it would appear larger than the full moon in our sky, a vast invisible shield and arena that stretches over 5 million kilometers in the sun's direction, with a magnetic tail, a stretched-out shadow that may brush the orbit of Saturn. It is a shield against the solar wind, 1,000 times more powerful than Earth's, a realm of such intense radiation, trapped, accelerated charged particles that it would instantly fry any unshielded electronics and be fatal to life, a testament to the furious electromagnetic heart beating within the liquid metal interior. This magnetic field is not a static thing. It is alive, fluctuating, shaping the space around Jupiter, controlling the behavior of its moons, generating auroras at its poles that are larger than our planet and 1,000,000 times more energetic than our own northern lights. It is the voice of the metallic hydrogen ocean shouting its presence into the void. And so we descend further, through this eternal, churning, electrically stormy sea of liquid metal, for tens of thousands of kilometers, the pressure mounting to tens of millions of bars, the temperature to tens of thousands of degrees, until we approach the final, most profound mystery, the core. What lies at the very center of this labyrinth of exotic matter? For decades, the answer seemed straightforward, a satisfying conclusion to the core accretion story. Following that model, we envisioned a compact, incredibly dense nugget, a fossil seed perhaps 10 to 20 Earth masses in size, composed of the heaviest elements: iron, nickel, silicon, oxygen, rock, and metal, all compressed into a scorching, super-dense sphere under the ultimate, unimaginable pressure of the overlying layers. It would be a world within a world, a terrestrial planet buried at the heart of a gaseous titan, a secret stone at the center of a gaseous peach. It made perfect sense, providing a clear anchor for the planet's structure and formation history. But sense, as Jupiter continually reminds us, is a provincial concept, a comfort we derive from patterns observed on our own small world. The universe has no obligation to conform to our expectations of tidiness. The data from the Juno spacecraft, which spent years in a precise polar orbit mapping the giant's gravitational and magnetic fields, has systematically and decisively dismantled that neat compact picture by meticulously mapping Jupiter's gravitational field with unprecedented precision, tracking tiny Doppler-induced wobbles in the spacecraft's radio signal as it was tugged by the planet's uneven mass distribution, a technique akin to a planetary CAT scan. Juno has painted a portrait of the interior that is fuzzy, diffuse, extended, and profoundly strange. The transition from the liquid metallic hydrogen layer to what we call the core is not a sharp boundary. There is no clear-cut surface, no distinct, crisp interface where liquid metal ends and solid rock begins, no hard floor to the metallic ocean. Instead, the core appears to be dilute or fuzzy. It is not a compact sphere, but a vast, diffuse region that may span up to half of Jupiter's radius, a bloated, indistinct blob of mixed materials tens of thousands of kilometers across. Scientists now believe it is more like a thick, dense soup, a gradual gradient or emulsion where heavier elements, rocks, ices, metals, are dissolved, suspended, and mixed into the liquid metallic hydrogen matrix, like chocolate syrup swirled into milk, but on a scale of worlds. There is no clean separation of substances based on density, as one might expect from a settled, differentiated planet. It is a planetary emulsion, a churning, partially mixed melange, where the very definition of core loses its traditional meaning. The heavy elements are there, in abundance. Juno confirmed Jupiter is enriched in heavy elements compared to the Sun, but they are not concentrated in a distinct compact sphere. They are stirred throughout a vast central volume, with no clear boundary between where the planet's envelope ends and its heart begins. The core is not a thing, it is a region, a state of mixing. This revelation forces a radical rethinking of Jupiter's formation and its subsequent history. How did this fuzzy, bloated core come to be? Is it a standard feature common to all hydrogen-helium gas giants, a necessary outcome of their formation physics, or is it a unique quirk of Jupiter, a product of its specific history in our solar system? We have not yet studied Saturn's interior with the same precision, though initial data from the Cassini mission's grand finale orbits hints it may have a similarly fuzzy, extended core. Uranus and Neptune, the ice giants, are compositionally different, with much thicker layers of water, methane, and ammonia ices over a smaller rocky core, and likely have more distinct, compact central regions. So, this diluted, indistinct heart might be the norm for true hydrogen-helium giants like Jupiter and Saturn. But if it is unusual to Jupiter, or if its specific fuzziness is unique, what singular event or process could have caused it? One compelling, dramatic, and aesthetically pleasing hypothesis points to a catastrophe in the solar system's violent youth. The early days of our planetary system, the first 100 million years, were a shooting gallery, a time of chaotic crossing orbits and giant impacts, the final act of planetary assembly. We see the evidence etched on our own moon's cratered face, on Mercury's scarred and wrinkled surface. What if, in that era of celestial bombardment, a fledgling Jupiter, still forming and hot from accretion, was struck a glancing or head-on blow by a protoplanet of immense size, a rocky or icy world, perhaps 10 times the mass of Earth, a super-Earth or a massive planetary embryo that had formed elsewhere in the outer disk. A head-on or near head-on collision of such magnitude would have been an event of almost unimaginable energy, far greater than the impact that formed our moon. The impactor would not have simply buried itself. It would have been vaporized, shattered, and partially merged with Jupiter's own primordial, perhaps more compact core. The titanic energy of the crash would have acted like a colossal mixer, stirring the central regions with ferocious turbulence, mixing the heavy elements of the core with the overlying envelope of liquid metallic hydrogen, diluting the core and creating the vast fuzzy gradient we infer today. This cataclysm might also help explain Jupiter's extraordinary mass relative to its location. The impact could have injected so much heat energy that it temporarily inflated the planet's outer layers, reducing its density and allowing it to more efficiently capture and retain even more of the primordial hydrogen and helium from the surrounding nebula before the young sun's radiation blew it away, supercharging its growth in a way its sibling Saturn could not match. The giant impact theory is elegant, dramatic, a story worthy of the king of the gods, a myth of creation through violence. It makes intuitive narrative sense, but does it hold up to the cold mathematical scrutiny of physics and simulation? Recently, astrophysicists, armed with sophisticated hydrodynamic simulation software and powerful supercomputers, decided to test it rigorously. They modeled countless scenarios, programming virtual planets of various sizes and compositions to slam into a young forming Jupiter at different angles, speeds, and stages of its growth. At first, the results were encouraging, even thrilling. A giant impact did create a fuzzy, diluted core, exactly as the theory predicted. The violence of the collision stirred the central regions into a churning, mixed soup, blurring the boundary between core and envelope. But then, as the simulations ran forward in time, modeling the aftermath over millions of years, a significant problem emerged. In every single run, the fuzzy core did not remain fuzzy. Over a period of mere hundreds to a few thousand years, a blink in geological and planetary time, the heavy elements, being denser than the surrounding metallic hydrogen, would settle back out of the mixture. Gravity, the great organizer, would resort the mess, The rocks and metals would rain down through the liquid metal in a process called sedimentation, reconcentrating at the center, reforming a distinct, dense, compact core. The simulation suggested that a one-off giant impact, while it could create a temporary dilution, could not explain a persistent billion-year-old fuzzy core. The planet's interior physics would erase the evidence of the crash on a relatively short timescale. Something else must be at work to maintain the fuzziness, perhaps a continuous process or a fundamentally different initial condition altogether. So, we are left with a profound and humbling paradox at the end of our descent. We have journeyed from the frozen sunlit cloud tops through an ocean of liquid molecular hydrogen 20,000 kilometers deep into a sphere of liquid metallic hydrogen 40,000 kilometers thick, and arrived at a central mystery that is diffuse, ill-defined, and enigmatic. We know, from Juno's exquisite measurements, that Jupiter has this big, weird, fuzzy core, a central region of mixed materials without a sharp boundary. But we do not yet know with certainty how it got there, or why it persists over the age of the solar system. The very formation story of the planet is called into question, suspended between two paradigms. Did it form via a modified core accretion, but with a twist we haven't yet conceived? Perhaps the core formed slowly and asynchronously, allowing heavy elements to be mixed upward by powerful convection before they could fully settle to the center. Or does the top-down gravitational instability model hold a key, producing a planet that was always more homogeneous from the start, with heavy elements distributed throughout the collapsing clump, leading to a fuzzy core by default? Or was there not one giant impact, but a series of smaller, successive impacts that kept the core region stirred? Or is there a different kind of internal process at work, like layered convection or double diffusive instabilities, where materials mix not just by heat, but by compositional differences that act as a planetary mixer, creating a stratified gradient and preventing the core from ever sharpening into a distinct object? The data has ruled out the simple, compact core. It has not yet provided a single, unambiguous answer for what replaced it. For all that we have learned, for all the stunning imagery, the daring spacecraft missions, the brilliant theoretical work, we still have no clear, definitive, universally agreed upon answer on how a planet like Jupiter is created in the first place. It stands as a monument to our incomplete knowledge, a giant striped question mark hanging in the sky, a reminder that for all our intelligence and ingenuity, the universe retains deep reserves of mystery. And that is precisely what makes it so compelling, so cool, in the most profound and awe-inspiring sense of the word. Its very existence challenges our categories, our models, our comforting stories of origins. It is weird, gloriously, magnificently weird. It is a giant mystery woven into the very fabric of our solar system, a mystery that has watched over the Earth since before life crawled from its oceans, a mystery that will likely outlast our species, our civilizations, perhaps even our star. But the mystery of Jupiter is not merely a planetary one, a puzzle confined to our own cosmic backyard. It is a cosmic signature, a template for a fundamental class of object. When we look at Jupiter, we are not just looking at one world, we are looking at the archetypal gas giant, the exemplar of its kind. Thousands of such worlds have now been discovered orbiting other stars, the searing hot Jupiters that hug their suns in days-long orbits, the cold Jupiters in distant year-long orbits, the rogue giants drifting between stars. Understanding our own is the master key to understanding this fundamental class of planet in the galaxy, to interpreting the data from distant exoplanetary systems, to building a general theory of planetary formation and evolution. Furthermore, Jupiter's existence and its specific history were likely the decisive sculptor of our solar system's habitability, of the possibility of our own existence. Its immense gravity during the early days may have hurled comets and asteroids rich in water and prebiotic organic material inward toward the early Earth in a process called the Late Heavy Bombardment, potentially seeding our barren world with the volatile ingredients for oceans and life. Later, as the solar system settled, it may have acted as a gravitational shield, ejecting dangerous leftover planetesimals and asteroids out of the inner system or into the sun, providing a quieter, more stable stage for life to evolve and flourish over billions of years. It is both a potential bringer of life's ingredients and a protector of its cradle, a silent guardian whose influence, for good or ill, shaped the destiny of our pale blue dot. As we look to the future, Jupiter will continue to beckon, a siren song of mystery written in gravity and magnetic fields. Future missions may deploy atmospheric probes or drones that can survive longer, deeper descents into its atmosphere, directly sampling the transition zones from gas to liquid, or even attempting to measure the properties of the metallic hydrogen layer indirectly. Advanced orbital observatories, perhaps with neutrino detectors, or even more precise gravity mapping instruments, will peer at its deep heat flow and internal dynamics in even finer detail. Theories will be refined, computer simulations will grow more complex and physically realistic, incorporating magnohydrodynamics, sophisticated equations of state, and complex chemistry, and perhaps one day the fuzzy core will yield its secret, and we will understand the precise sequence of events that forge this king of planets. But even then, when the scientific mystery is solved, Jupiter will retain its essential majesty, its elemental strangeness, its power to humble and inspire. It is a world where gas becomes an ocean, where an ocean becomes a metal, and where a metal generates a magnetic field that could encapsulate the sun. It is a world of storms that last millennia and oceans deeper than planets. It is a perpetual experiment in extreme matter, a fluid sculpture shaped by rotation and gravity. It is the ultimate reminder that the universe is not just stranger than we imagine, but stranger than we can imagine, constantly exceeding the boundaries of our models and the limits of our intuition. It floats in the silent dark, a striped sentinel, a fluid giant, a perpetual enigma, a beacon not just of reflected sunlight, but of profound mystery, asking us with every 10-hour rotation to look deeper, to think harder, to venture farther, to question our assumptions. And we will, for the mystery itself is the invitation, and the journey to understand it, with all its false turns and stunning revelations, is a fundamental part of what it means to be a conscious, curious entity on a small rock, orbiting a modest star, living forever in the shadow and under the protection of a giant.